Hi everyone. This talk is about interior point methods with a gradient oracle. We are interested in solving large classes of convex programs such as linear programs, semi-definite programs, hyperbolic programs, and so on. These capture many fundamental problems that we need to solve on a regular basis. Obviously, they have applications in algorithm design since many standard problems can be cast as solving a linear program. But more importantly, these primitives show up in very practical instances such as engineering, scientific computing, economics, transportation, or logistics. Since these problems are ubiquitous, there are many ongoing efforts to provide solvers with improved theoretical and practical guarantees. To give a bit more insight about this result, let me first describe the main approaches people use to solve convex programs. We will consider a specific case of linear programs since they represent the simplest example. Note that we are interested in high-precision solutions. There are some classes of approximation algorithms that achieve fast running times, but their running time depends polynomially on the target precision, so they are very slow for high accuracy. Here we depend logarithmically, so we can solve to machine precision with only a logarithmic overhead. Standard methods for solving problems like these, which achieve the state-of-the-art as far as theoretical or practical runtimes are concerned, are cutting plane methods, or ellipsoid methods, and interior point methods. The latter are hugely popular because in practice they are very fast. Also, many state-of-the-art algorithms for fundamental problems are based on interior point methods. This is the focus of our talk. Now let me briefly explain what is an interior point method, or an IPM. It's a primitive that reduces convex programming to a sequence of calls to Newton's method, or in other words, to solving a sequence of linear systems of equations. Again, consider the case of linear programs for simplicity, and suppose we want to solve the problem minimize C inner product x such that AX is greater than or equal to B. Think of the polytope in the image as the convex set defined by the linear inequalities, and think of the C vector as a vector pointing downwards. So we are trying to find the bottommost point in this polytope. If you ever worked on optimization, you'd notice that the main difficulty here is that the inequality constraints make the problem very hard. What IPMs do is that they replace this constraint with a convex penalty function called barrier function, which acts as a repelling force that pushes us away from the boundary of the domain, and it explodes as it approaches the boundary. Using this, we define the family of functions parameterized by a scalar mu, f mu of x equals C inner product x plus mu times phi of ax minus b. We intend to minimize f mu for a very small mu, which means that while phi keeps us in the interior of the domain, its contribution is negligible. It is very hard to minimize f mu directly for a fixed mu. Instead, we consider the family of minimizers for all mu in the interval 0 infinity, which define the central path. Minimizing it for large mu is easy, for very small mu is hard. What we do is that we follow the central path. By this we mean that we run a sequence of optimization problems called progress steps as follows. For each such problem in the sequence, we warm start it with a point on the central path corresponding to the minimizer of f mu times 1 plus delta. From here, we try to find the minimizer for f mu, a function in the family with a smaller barrier parameter. How do we compute these progress steps? For each of these progress steps, we run a sequence of greedy iterations to minimize f mu. The idea is to move from an iterate x to x plus delta while decreasing the value of f mu. How to do this? We Taylor expand f mu around x. So we approximate the expansion with a degree 2 polynomial by removing the higher order terms and move in the direction of the minimizer. This is what is known as Newton's method, which is a second order method because it expands f mu to the second order. The computational difficulty with this is that the step is obtained by solving a linear system involving this matrix of second-order derivatives called the Hessian matrix. This requires first computing the Hessian, and secondly, solving a linear system involving the Hessian. Now, as you may know, solving linear systems is very difficult and is a mix between art and science. There are ample works dealing with this problem alone. There are many clever algorithms implemented in standard software packages, and yet there is no silver bullet since the performance of these algorithms heavily depends on the structure of the input. But practitioners love first-order methods, which use only gradient information and do not even attempt to compute the Hessian. This is obviously less informative since we lose information about the local curvature of the function, but maybe we can still make informed guesses based on the gradient history. Related to this, there has been a lot of cool literature on what is known as quasi-Newton methods, among which we can enumerate BFGS, LBFGS, ADAGRAD, or KFAC, which attempt to recover the performance of second-order methods while only using gradient information. It is natural to attempt to do so for general convex optimization. This is the question we address here by providing an efficient algorithm with formal guarantees. So the question we are asking is whether we can solve convex programs efficiently using only gradients. The answer is yes, and in fact we can obtain speedups over second-order methods in certain interesting regimes. Formally, we can prove the following. Given a convex set K, which is well-conditioned for some appropriate notion of well-conditionedness, and which is endowed with an appropriate barrier function phi, we can minimize linear objectives over K in time t plus n squared times square root of n times nu, where t is the time to evaluate the gradient of the barrier, and nu is a specific parameter of the barrier function, which we should think of as order n. Let's see what this means in specific examples. For the case of linear programs, we obtain an algorithm that only needs to compute O tilde of n gradients and pays an additional overhead of n cube. While these results are incomparable, this parallels the state-of-the-art for convex programming using the cutting plane method, only that in their case they use a separation oracle, while here we assume access to an oracle that computes gradients. For the case of semi-definite programs involving n by n matrices and m constraints, we obtain a running time whose dependence in m scales like m to 1.25, whereas all previous solvers scale like m squared at least. This improves over these algorithms in the case where the number of constraints is very large. Now let's talk a bit about the approach we use for our algorithm. The fundamental problem we have to face is that even though we are aiming to minimize some convex function without looking at the Hessian, it's not even clear how to do so for quadratics, or equivalently solving linear systems. Formally, suppose we want to solve a linear system Ax equals b, but we never want to write down the matrix A. The only type of access we can assume is that we can evaluate matrix vector products. The simplest approach for solving such systems is an iterative method called the Richardson iteration. It starts with some guess for the solution and iteratively attempts to improve it by moving it in the direction of the error or the residual. While this method is very nice and simple, there is a major downside, that is, the number of iterations depends on the condition number of the underlying matrix, which may be huge. So this will not be efficient in general. On the good side, we can improve the state of affairs by using what we call a preconditioner. This is a matrix A tilde, which approximates A for the right notion of approximation, and for which we have access to its inverse. Plugging this matrix inside the Richardson iteration gives us extremely fast convergence. The obvious question that pops up is how do we obtain such a preconditioner? The answer is that maybe we can learn it from past iterations. To illustrate this idea, let's imagine that we are using a preconditioner A tilde and we are executing one step of the Richardson iteration. There are two cases to consider. In the first one, the iteration makes a lot of progress since we see that it reduces the error by a lot, so all is good. In the other case, the iteration does not make a lot of progress. But the reason why this happened is that A tilde was poorly aligned with A. Furthermore, we know that they are poorly aligned along the direction of the residual, since otherwise we would have made progress. So we use this information to improve A tilde. What does it mean to improve it? We need some quantitative notion of how well they approximate each other. Luckily for us, Donegan and Harvey, in a beautiful work where they were attempting to construct preconditioners based on the conjugate gradient method, came up with this nice potential function. What's the intuition for this? In the excellent case where a and a tilde match exactly, both terms under the determinant equal the identity. And we are looking at log determinant of the identity, which is 0. If they do not match, one of these two terms will contribute significantly to the potential function. What is nice about this potential function is that based on the information we learned from a step where we did not make much progress, we can update a tilde and its inverse via rank 1 update such that potential decreases by a constant. This is great for solving a single linear system since each failed step triggers a decrease in potential, and there cannot be too many of these. Now let's briefly illustrate the main ideas of Donegan and Harvey for maintaining a preconditioner. First, suppose without loss of generality that the preconditioner is the identity matrix and we execute a step of the Richardson iteration with a step size eta. We pick the step size to minimize the norm of the residual, where by residual we mean the difference between the right-hand side vector b and a multiplied by the current vector xt. By expanding the squared L2 norm, we see that we can minimize the norm of the new residual by picking an appropriate step size eta as written in the box, which plugged back in shows that we make multiplicative progress. Note that the term above the brace would better be large, so we make large multiplicative progress. If it happens to be small, then there are two possibilities. Either the ratio between the a squared norm of the residual and its a norm is large, which equivalently shows that a is far from the identity because it must have a large eigenvector, or similarly we obtain a certificate showing that a must have a small eigenvector. In what follows, we will focus on this case since the other is similar. The point is that we want to use the certificate to update our preconditioner in such a way that the potential function decreases. To understand how to do so, we first rewrite the potential function in a more convenient form just by using the nice properties of the determinant. And note that after performing a rank 1 update to the matrix A, we can exactly write down by how much it changes. Whenever u, the vector we use for the rank 1 update, is a unit vector, we obtain an upper bound that shows that it decreases whenever u certifies the existence of a small eigenvector for A, or in other words, the quadratic u transpose A inverse u is large. Since the potential function is really nice and symmetric, we can further show that doing a rank 1 update on A has the same effect on the potential function as doing a rank 1 update on the preconditioner. In this case, we replace u with the vector a to 1/2 times the residual, which is the certificate that shows that a has a small eigenvector. This settles the case of solving a single linear system, but in our case we need to solve many linear systems, corresponding to the different points on the central path that we get to visit during the interior point method. The good thing about these is that their corresponding matrices are slowly changing. In fact, we can show that once we move to the next linear system in the sequence while preserving the old preconditioner, the potential function can only increase by a constant. Let's see why this is the case. Consider the case where phi is the logarithmic barrier. The linear system we will solve will have the form A transpose times diagonal of st to -2 times A, where st is the vector of slacks ax minus b. It is a standard observation that when we advance down the central path by changing the centrality parameter mu to mu times 1 minus 1 over order m, where m is the number of inequalities, slacks change multiplicatively by a factor 1 plus rho, where rho is a vector whose L2 norm is at most m to -1/2. Now imagine for a second that A was the identity, and we also used an identity preconditioner. Then we could write the initial potential function as logarithm of product over all coordinates of 1/2 times square root of slack I plus 1 over square root of slack I. And the potential function after h gets updated looks as follows. The worst case increase in the potential function happens when all rows are about 1 over m in magnitude, in which case the contribution of each slack to the potential increases by a factor of 1 plus 1 over m, and hence potential increases by a constant overall. We can show that this intuition actually holds in general, even when the matrix of slacks is squeezed between some A transpose and A. To prove this, we need to use some interesting tools from matrix analysis involving majorization and Schur convexity. Now, the fact that the Hessian increases the potential by very little is not only true for the logarithmic barrier, but actually for any barrier that satisfies this technical property called strong self-concordance, as defined in a paper by Lada, Lee, and Vempala. Intuitively, strong self-concordance says that when taking a step, the Hessian matrix of the barrier function phi suffers a small relative change in Frobenius norm. This is stronger than what standard self-concordance gives, which bounds the change in spectral norm. In fact, it has been shown that this property is satisfied by very good barriers, which give an improved number of iterations of the interior point method, such as the universal barrier or the entropic barrier. The fact that they satisfy this stronger property is not immediately clear, but it actually follows from recent progress on the KLS conjecture. So there's a whole bunch of deep theory buried underneath this innocent-looking potential function. Now, to wrap up the analysis, again let's look at the case of linear programs with n variables. If we use a good barrier inside the interior point method, we solve a sequence of O tilde of n linear systems using the Richardson iteration with a changing preconditioner H tilde. There are a few cases to consider. In the good one, H tilde approximates H well, so we can execute an iteration very fast in quadratic time, which is the time required to apply the inverse of the H tilde operator, provided we have it written down. If we fail to make much progress, then we update the preconditioner H tilde and its inverse via rank 1 update. Using the Sherman-Morrison formula, we can do this thing in quadratic time, and this operation decreases the potential function by a constant. Finally, when we move to the next linear system, the potential increases by at most a constant, as shown earlier. Now, provided that we initialize the method with a decent preconditioner so that the initial potential is at most O tilde of n, over the entire course of the algorithm, the potential still stays below O tilde of n because of the third bullet point. This also means that there are at most O tilde of n preconditioner updates, since each of them decreases the potential by at least a constant. Hence, we see that in each of the O tilde of n steps, in total, we make a gradient query in time t and pay extra quadratic overhead, hence our final running time. Finally, it's time to draw some conclusions. We provided a quasi-Newton method for solving general convex programs. Furthermore, it achieves optimal gradient complexity for solving linear programs. And it is an interesting question whether the overhead of n cubed can be reduced. If we analyze things carefully, we can show that our method improves semi-definite programming in certain regimes. And probably there are a whole bunch of other interesting examples like solving SOS programs. Finally, this gives a powerful framework for constructing preconditioners. And of course, there is a lot to improve here. For example, I'd be curious if it's possible to maintain a preconditioner more efficiently or succinctly than just updating it in quadratic time via rank 1 updates. That's all for now. Thank you for watching.